Performing A-scan biometry with Quantel ultrasound systems. In this brief video, we'll review the fundamentals of performing A-scan biometry with ultrasound equipment from Quantel Medical. We'll cover the basic physics of ultrasound, equipment features, and the process of obtaining a reliable reading. Basic physics of ultrasound. Medical ultrasound involves the transmission and reception of high-frequency sound waves for the purpose of imaging and measuring internal anatomical structures. The A in A-scan stands for amplitude. When looking at an A-scan image, the amplitude of reflected sound is represented by the height of the spikes. Amplitude describes the magnitude of the pressure change of a sound wave. If the sound were in the audible range, the amplitude would reflect its volume or loudness. Frequency, measured in hertz, is the number of oscillations per unit of time. As the name suggests, ultrasound frequencies are well above the level that can be perceived by the human ear, that is, greater than 20,000 hertz. The A-scan probe emits sound at a frequency of 8 or 10 megahertz, 8 or 10 million hertz. Velocity refers to the speed at which sound moves through a structure such as air, water, or tissue, and it depends on the density and compressibility of that medium. Generally, the denser the medium, the more quickly sound waves travel through it. The velocities of sound through specific tissues and implants have been determined. For example, sound's velocity through air is relatively slow, at 331 meters per second. Through soft tissue, it's faster, at 1,550 meters per second. And through bone, a relatively dense medium, sound travels quite fast, at 3,000 to 5,000 meters per second. The velocities of sound through intraocular tissues have also been determined. In the anterior chamber and through the vitreous, sound travels at 1,532 meters per second. Through the normal lens, 1,641 meters per second. In the pseudophakic eye, the speed varies according to the material properties of the intraocular lens. The velocity through an IOL made of PMMA is 2,718 meters per second. Through an acrylic IOL, 1,946 meters per second, and through a silicone IOL, 1,050 meters per second. These values are typically integrated as defaults into the analysis software of ophthalmic ultrasound devices. It is useful to know the standard dimensions of the eye for comparison against the measurements obtained on a biometry scan. The total axial length, the distance between the anterior corneal surface and the retina, is typically about 23.5 millimeters. Shorter axial lengths correlate with hyperopia, and longer lengths with myopia. The total axial length is the sum of the length of the anterior chamber, lens, and vitreous, which measure on average 3.24 millimeters, 4.63 millimeters, and 18 millimeters respectively. Equipment features. We will now review some of the features and techniques for using Quantel Medical's Aviso ultrasound system to perform A-scan biometry. The Aviso is a modular ultrasound platform featuring a portable, compact main unit with a user-friendly touchscreen connected to a laptop or desktop computer through a USB cable. Image acquisition can be controlled via the touchscreen or the computer, where data and images are displayed. Press the Biometry A icon to access biometry mode. From the A-scan biometry screen, the examiner can select the parameters appropriate to a given patient. The type of probe. We'll choose the standard biometry probe. Eye type. Whether the patient's eye is phakic, aphakic, or pseudophakic, plus the IOL material. The acquisition mode. Manual or auto. And the technique. Contact or immersion. When the exam is in progress, the image area at the center will show the A-scan being captured, and the result area on the right will list the measurements obtained. The examiner can adjust the gain and dynamic by turning the gray knob at the front of the Aviso unit, or by clicking the plus and minus signs in the gain field on the left side of the screen. A measuring cursor can be positioned manually for more precise or additional measurements beyond what is captured in automatic mode. The software also allows the examiner to review the scans obtained in automatic mode and delete any outliers or suspect results. The Aviso is equipped with 6 IOL calculation formulas, including the SRK2, SRKT, Binkhorst 2, Holiday, Hoffer-Q, and Haggis. Once patient data has been entered and scans have been obtained, the IOL calculation can be performed. Selecting the IOL icon opens the IOL calculation screen, where formulas can be selected from a drop-down menu. Contact versus immersion. For A-scan biometry of normal eyes, two methods of probe placement may be used. In the contact or applanation method, the probe is placed directly on the cornea. In the immersion method, the probe is placed over the cornea in a fluid interface contained by a scleral shell. The contact method is often considered the easier way to perform biometry, but its essential pitfall is that touching the probe to the cornea can cause compression of tissue, resulting in an axial length measurement that is falsely low. Such discrepancy can contribute to errors in IOL selection and suboptimal post-operative refractive outcome. To minimize corneal compression and error, contact of the probe on the eye should be very light. The immersion technique is generally considered more accurate for axial length measurements since the cornea is not compressed. A small shell is placed beneath the lids and filled with coupling medium such as methylcellulose, and the probe is immersed in the liquid close to but not touching the cornea. This technique involves a slight learning curve. Scleral shells come in different sizes that correspond with a range of corneal diameters. The Prager shell, seen here, is only one of many brands of scleral shells. This particular shell comes in one size only. The Prager shell is fitted with single-use disposable tubing for infusion of fluid from the side via a plunger. The shell itself must be disinfected between patients, and the tubing discarded and replaced. For other shells, the coupling medium must be poured into the top of the shell with one hand, while the other hand stabilizes the shell on the eye. Each examiner should find the method that works best for them. Features of a good scan. IOL power calculations should be based upon the best scans obtained, and suboptimal scans should be discarded. So the examiner must know the features of a good scan. A good scan is characterized by steeply rising, high-amplitude peaks corresponding with the cornea, the anterior and posterior surfaces of the lens, the retina, and the sclera. A good scan also includes the deepest anterior chamber measurement. When using the contact method, the deepest anterior chamber measurement is associated with the least corneal compression. Finally, the examiner should select the thickest lens measurement because the lens is generally thickest in its center. Using the highest value for lens thickness helps to ensure that the ultrasound beam was directed nearest to the center of the lens. Process. With that in mind, we turn to the process of performing A-scan biometry. First, explain the procedure to the patient and answer any questions to ensure they feel relaxed and ready. Obtain the patient's keratometry readings and enter them into the system. To perform either the contact technique or the immersion technique, the patient should be reclined. A topical anesthetic should be applied to both eyes. Ensure that the correct probe is cleaned and ready to use, and that the rest of the ultrasound device's settings are correct. Check the primary eye to indicate the eye that you will measure first. Remember to always measure both eyes. The parameters of the eye can be changed by using the drop-down lists at the top of the screen. Choose the eye type, phakic, aphakic, or pseudophakic. And for those who are pseudophakic, indicate the IOL material, PMMA, acrylic, or silicone. Now, perform a series of scans. A maximum of 10 may be obtained within a period of about 30 seconds in automatic mode. Remember that the machine is recognizing high signals, so it is vital to evaluate each scan obtained to confirm that the appropriate spikes have been measured. At least 3 measurements are needed for the IOL power calculation, and more may be used depending on the protocols of individual clinics. It is critical to examine the total axial length and anterior chamber measurements for consistency. The standard deviations for each should not exceed 0.1. Then perform the calculation using the desired 2-variable formula, SRKT, Holiday, or Hoffer-Q. A constants provided by IOL manufacturers or personalized for the individual surgeon may be entered and included. It is important to note and use the correct A constant for each IOL, as manufacturers commonly provide both an ultrasound A constant and an optical A constant to be used with optical biometers such as the IOL Master. Supplemental B Scan. Under some circumstances, one-dimensional A-scan biometry should be followed by a two-dimensional B-scan. If achieving perpendicularity to the eye structures is difficult, or if an unusual spike is present and does not disappear with repeat scans and adjustment of the probe's position, performing a B-scan is strongly suggested to rule out the presence of an abnormality that may be causing the difficulty. To recap, in this presentation we discussed the basic physics of ultrasound, the equipment features of the Aviso system, contact versus immersion methods of biometry, features of a good scan, the process of axial length measurement and IOL calculation, and indications for performing an additional B-scan study. Quantel Medical's exemplary ultrasound technology has brought multiple innovations to ultrasound specialists worldwide since 1993. We hope you've found this demonstration of A-scan biometry using the Aviso helpful. For more information about this technology and Quantel's complete range of diagnostic ultrasound products, please visit www.quantel-medical.com.